August. Perfect. So generally, what we are trying to address today, and there are a couple of colleagues from Intel, T-Mobile, from ONF, is to discuss about OMEC in the context of T-Mobile Poland production code release. It is split actually in 2 days. So today we will cover the first part. The second part will be on 25th of March. And I think that, I don't know, August, if you would like to say a few words on just setting up the stage, then I could continue with the project background slides.
Sure. Thank you, Michal. I'm very excited to actually be participating in this webinar. As you know, the OMEC open source project within ONF has started with the seed code from Intel and Sprint. And since then, we have, in a very short amount of time, we have progressed greatly. And this is evidenced definitely by the T-Mobile Poland productization and all of the efforts that the team, along with Intel, have put forth in turning this into a hardened, production-ready solution. So we will be hearing all of the efforts that T-Mobile Poland and the associated ecosystem have put forth to make this a reality. And to my knowledge, this is the first of its kind, in the sense that this is the first time a tier 1 operator is actually using an open source mobile core in their production networks. So I'm very excited to be part of this, and I look forward to the workshop.
Perfect. Thank you very much. Any additional introductory words from the colleagues from Intel or anyone else? Okay, if not, then maybe I will just share the screen. So exactly, perfect. Great. So first question is, can you see my screen right now?
Yes.
Perfect, fantastic. So we can start. So my name is Michal Sewera. I was for a very long working in T-Mobile. Right now I am part of the MobiledgeX, which is Deutsche Telekom spin-off, working on edge computing. But for the last 2 years with the colleagues from T-Mobile, we was working on the potential use case around open source EPC. And of course, we was extensively working together with the colleagues from Intel, and the baseline was coming from Open Networking Foundation. And I just want to show a couple of slides just to set up the scene and just to explain what was the background and why we started with this. So first of all, trying to answer the question like why open source? Actually, there are a couple of other approaches. You could ask the question why open source and why open source now? Because theoretically you could say that it was available for quite a long time, especially looking from a more IT world perspective. And I would just like to highlight a couple of very important factors which are contributing to this. So first one is a completely new business model. As it's stated, it's all about transparency of software deliverables. Means it does not mean absolutely for free. It just means the operator has more visibility to what is really happening in the code. And this sort of model is already used in different domains, like, you know, coming from IT world. Now, the other focus is, of course, upcoming 5G, which is very much pushing towards the third-party solutions and exposing the network capabilities. We have new interfaces like network exposure function. And if we'll add to this the already visible trend towards network function virtualization, that all creates an environment which very much supports open source models. And that was exactly the reason why we said, okay, if this is possible right now for an IT domain, and we already proved that NFV, so network function virtualization, can really work, leveraging the same technologies like for IT, using KVM, using acceleration for a data plane like DPDK, SRIOV, why we should not just try this sort of new model. And especially considering the fact that EPC is really around, becoming a commodity as a base layer for majority of the services. So just to add a couple of more thoughts on it. So of course, open source does not mean for free, but open source also means that there are a couple of properties which you just check in the context of your organization. And this is also very much in line with what was happening in an operator industry over a couple of last years. And this model, which I'm presenting here, this is so-called 12 factors models. It's properties of cloud native apps, which need to be changed or checked actually, before it's deployed in terms of checking your organization. And I think that we was all observing a very strong movement on an operator ecosystem towards more agile frameworks, when you have more agile way of working, including sprints, including more cooperation with the IT sort of environments. I think here about all the methodology for testing, for verification, for actually even maintaining the code, checking the code. So I think that this last couple of years very much supported the way of collaboration between operators, suppliers, and a third-party independent application vendors. And I think that this is very much in line with the trends for other network functions virtualizations, not only EPC, but we selected specifically EPC, and that's exactly what this slide is explaining, just because we thought that this is really a very good use case around it. So in terms of a high-level strategy and main assumptions, the key proposed was to base on a very simple service. It's called fixed mobile substitution or fixed mobile convergency. It's available in the different markets, but the base principle is to have a very small subset of EPC features, which potentially they are quite easy to be implemented, and start just with this like a minimum viable product. Just focusing on a very highly efficient platform in terms of megabits, gigabits per second, but with a very minimum set of features. And that was exactly the background for this activity. So first of all, the thought like, okay, if we are already network functions virtualization, then we could try to use different model like open source. And if open source, then let's just try to use, to focus on a use case, which will be very supportive in terms of possibility of success. Because the worst case would be to start with a very complex scenarios and create a very classic project like a waterfall with thousands of different features, potentially long testing, and it will be very difficult then to get to the point when this will be proven to work. Here, the concept was completely different. Let's start with a very simple approach. Let's try to present, first of all, the capabilities for stability of such a platform. So let's implement something which can prove that it can fly in a network without the crashes. Let's observe and learn on it. And based on this seed, try to build additional things. So that was exactly the very high level strategy assumptions when we were starting this journey. So that's exactly the FMS EPC use case. My colleagues from T-Mobile will have more dedicated slides on it, so I will not go through it in detail. It will be available later just to review. But that's exactly the business use case which we selected to start with this exercise. In terms of the platforms, so when we are saying keyword EPC, what does it actually mean? If you think about really this FMS use case, the real pain point is actually initially not the MME, it's not the PCRF, it's not the HSS, Typically for fixed mobile substitution or convergence, the big problem is throughput. And when you say throughput, actually then, of course, the usual suspect will be gateway. And in terms of the gateway, looking from the OMEC perspective, so we have serving gateway and packet gateway actually sitting as a single entity in terms of the physical allocation. So the assumption was initially very simple. Let's do not go even into, you know, geographically distributed control plane and user plane. However, of course, you know, technically possible. But let's just focus on a very basic scenario when we will have a slice or a chunk of the capacity for the system available in a single place, and we could use a very simple mechanism which is available actually for a long time, related with ability to steer the traffic accordingly. And that is because of this APN and subscriber charging characteristic profile. So then using APN resolution extension mechanism or other different mechanism, actually this is just a very simple example, you can select a fraction of your traffic to put it into a new gateway. And that is extremely important because you don't need to then prepare your entire network in terms of the capacity to do a big switch off or switch on in a certain day. But you could say like, okay, let's just select only a, you know, initial few subscribers and let's just try to practice with them. And that was exactly the idea. So to conclude, to select only a very small subset of this entire EPC, focusing on a gateway part. Secondly, to use a network mechanism in order to route the traffic only for the relevant subscribers which we want to switch into a new box. And then we have a full process, full control of the process related with switching over from left to right. So that was exactly how it was planned. Now, in terms of the future, in terms of the features like this minimum viable product subset. Of course, again, I will not go through in detail. There will be much more extensive session by colleagues from T-Mobile Poland later. But this slide just presents the majority of something which we could call a minimum viable product. So focus on critical interfaces required for SP gateway, focus on some generic functions, and also in terms of the configuration, focus on ability to really do a certain troubleshooting. Initially, when we started, there was much less ability to check what is really happening on the platform. In terms of carrier grade readiness, this is typically one of the most important factors to evaluate if this is something which we can use really in the production or only for a demo. So that was more the context. Of course, we was focusing only on 4G here. Just to simplify, as I said, it was a very minimum viable product set of the features. However, it is already prepared for the future use for 5G, at least for a basic strategy. Good. Now, the other point related with the question about, okay, features or quality. It was a very big discussion initially, okay, what to implement, what to put actually into a roadmap of the product in order to make it carrier grade ready. And our conclusion, and I think that that is key message, which will be extensively detailed during the next couple of slides by the colleagues, is all about this, because it's not about just putting a lot of new features and saying like, yes, we are, I don't know, compliant with 3GPP release X or Y, and still on a very basic level, we are not then fulfilling key critical operator requirements. Because then reality will show that whatever operator will try to use such a solution, it will probably tell like, okay, it's very nice, it's, you know, nice for a demo, but because, I don't know, it is not solving the problem related with performance, or it's not solving the problem related with traffic and packet handling, or I don't know, a basic diagnostic things, I don't know, fragmentation, those kind of problems, then it's, you know, not usable in the production environment at all. And here the context was completely different. Let's do not focus on those features which will be, you know, nice to have for the future, but let's just start with a very basic fundamentals, let's call it like this. And when I use the keyword fundamentals, I don't know, UE IP allocation, IP fragmentation and assembly, control plane and data plane CLI, and billing and lawful interception. Those four categories, let's call it like this, they are super critical in order to even start the discussion about ability to put the certain things in the production. And exactly that was it. So someone could say like, oh, okay, it does not support, I don't know, GX, GY, whatever. But I always believe that, you know, with the concept of start small and scale fast, that's always possible. It's not possible vice versa. So if you start with, you know, putting a lot of features without, you know, taking care about the fundamentals, and colleagues from Intel will exactly explain what does it mean talking about fundamentals and changing the architecture really to address the things related with slow path for signaling traffic, for a fast path, for a user traffic. That's all about. And that is the reason why we selected, first of all, quality, not quantity. But we believe that what we are trying to sell today to the world, the message like, okay, we have a first software which is production grade ready. It will be available in the repo. And we strongly believe that there will be other contributors, other operators taking it and working in a collaborative way to extend the other features. And that's exactly the key message which we're trying to present here. Of course, there was a lot of pre-work related with some demos. So for example, during last year NWC in 2019, it was presented on the ONF stage when we was able to demonstrate the functional separation between control plane and user plane. So if you will go, if you will do deep dive, actually, what is really capable, what is really possible from the platform perspective, you will easily discover that there is really significantly more which we are really even using in this production environment. I already mentioned that we are not using a geographical separation for a control plane and user plane separation. That's just the message like, okay, because we started with a very fundamental basics, it does not mean it's not intended to be scaled out considering the latest features, like for example, control plane and user plane separation. So specifically, CAPS was demonstrated exactly on MWC 2019. And colleagues from T-Mobile will of course take you further in the slides. That was just the slide which I was presenting on ONF Connect, I believe in 2000, around September 2019. And I think that we are, as an entire ONF community, very much in line with this high-level plan to start with an MVP, and that is exactly what colleagues from T-Mobile will present. Do the field trial with a very limited subset of subscribers, and then collecting and adding new features, extensively adding new perspectives. Specifically, I am working right now with the colleagues from ONF on the Ether platform when COMEC will actually be used as a component for connectivity platform, just to fulfill edge computing platform capabilities. But I'm pretty sure that there are a lot of other use cases which this software can fulfill. So that's it from my side, as just to set up the background. So now I will pass the voice to the colleagues from T-Mobile. Thank you very much.
Okay, thank you, Michal. So the fundamental question, do you see my screen?
Yeah,
Yes.
you can see it.
Okay. Okay, so welcome everyone that is attending this webinar. My name is Rafal Arciszewski. Let me introduce myself a little quickly. I am a mobile packet core expert, nearly 20 years in telco industry. I started in 2001. For 3 years, I work now in packet core DevOps team in T-Mobile Poland. I was dealing from operations from NMC stuff to routing, R4, packet core, so pretty much everything in telco industry. I'm a Python and Monty Python fan, casual gamer, and some activities like mountain hiking. The Witcher is the famous, the best game in Poland, so I recommend you to check it out. Okay, so about the agenda, I'm planning to say to you a few words about our cooperation with Intel Labs. After that, I will tell you about 2 use cases that Michal said that we started with FMS, but during this collaboration and work, we find out that this campus area use case is very in line with our what we have now. So then I will talk about the proof of concept that was made December last year. It was also announced via Open Network Foundation. And the last section is about the NGIC itself. So about its features, new features, bugs, and the performance. If anyone have a question, please put it in the question and answer. Maybe I will try to answer during or maybe after the presentation. Okay, so our cooperation started November 2018. We agreed scope of work. So Intel and T-Mobile, we were responsible together in architecture design and new features introduction or discussion, negotiation. Intel was committed to software design and code development. And we as a T-Mobile Poland give them our telco guidelines. We tested the software, reported bugs, and eventually put a POC. We established a dedicated software branch. It was taken from current master branch in ONF. But since the beginning, we knew that this code will be going back to the community. So there was no question that we will use and hide it for ourselves. We need to have a tools to cooperate with Intel because the time delay is killing us. So it's 8-hour time delay, and we can talk only early morning or late evening. So we established 3 tools: Jira for bug reporting and feature requesting, Bitbucket for software development, and Confluence for Wiki. Each week we had our status calls, and there was countless design, testing, troubleshooting, on-demand calls, which was a little bit difficult because of the time difference, but you cannot avoid it eventually. In our Jira currently, here is an status. So we identified 40 bugs. Most of them are squashed. We raised 12 improvements and 8 new features. Most of them are done. There are some tasks also to make the work moving forward. On the Bitbucket, currently I checked yesterday. We have I don't know, 5 branches. So there are some experimental branches like a live branch, and there are some more stable branches. And the number of commits, it's very big. So like 100 commits probably. So you can see that the work was moving very fast forward. About our business cases. First one is fixed mobile substitution. It is called in our marketing in Poland like home internet. It's a sales like home internet. Basically, it's a simple access to the internet, 2G, 3G, and 4G. And the home routers are delivered by T-Mobile to our customers. There are 2 flavors of tariffs. The old ones had no volume limits, so it was like unlimited internet access. It was the commercial slogan, unlimited internet access, but it was limited by the bitrate. So you could download everything, but you were limited to 20 megabits or 60 megabits, depending on how much you pay. But from the November 2019, it was changed, and new tariffs are limited in case of volume, but the bitrate is unlimited. However, after you deplete your volume, the bitrate is limited to 1 megabits per second in order for you to buy additional packages. Also, there is for heavy users, which are really downloading very huge volumes of data, especially for old tariffs, additional QoS priority was decreased. It was done by changing QCI parameter in the network. This service, the traffic scale of the service is like here. So its average user throughput is around 1 megabits per second, and we have several 100,000 users in the network. So we are dealing with several hundreds of gigabits per second. But this is very, very simple. There is no DPI, there is no fancy redirecting or something like this, no. Current status about this FMS project on the Open Gateway, Open EPC, is that like this, that we need one more feature to have it working commercially. It's low for interception. Currently, we have this development in progress on this experimental branch, and X1 and X2 prototype is working. So after the LI development, we needed to establish to find out the scalability model because of the huge traffic that potentially could be run on this gateway. We categorized this models like in 4. So one silo, it means that CP and DP pair sitting on the server alone. Multi-silo, so you have multiple pairs on one server. Local caps, it means that CP and several DPs, but they are on the same server. And the real caps, totally geographically separated CP and DPs on different servers. We chose this local caps for the design model. Based on that, we are planning to do our hardware cost estimation, and DC routers, firewalls, other surrounding components that are needed. After that, we will take a business decision because the tariffs changed, and there are some lacking functionality that we don't have now. So maybe we will introduce new tariffs, or maybe we will just cope with some lacking functionalities. After that, it will be probably deployed in the network. First in the for the few subscribers, and later in the larger scale. Scalability model, there's a question, is it configurable or is it compile time feature? It's not about the software itself, but it's rather like architecture design. So we designed that the CP and DP sitting on the same server. Okay. And here is our FMS Skylink example, how we see it as a T-Mobile. So basically, when we started this project, 1 year ago, we had in our minds Minion architecture concept. I call it microservices, contrary to the microservices architecture, because the concept is like this: you are putting in your network very large, very many little gateways, which I call Minion, and those gateways are very small, very simple, not reliable. But there are plenty of them, and in this way you can focus on the real on the basic functionalities which are Minions doing, so forwarding packets from S1U to SGI, but you do not care about the redundancy, because you assume always that 1 Minion, it's okay to fail. 1 Minion can fail, and other Minions will take over. So it was from the beginning that we do not require redundancy in the NGIC. We don't require complicated structure. So, for example, on one side I prepared scaling like this. So imagine that we need 160 gigabit traffic on a site, and for 256 kilo user sessions. And for that, you will need 2 EPC servers with SGX and DPTK, 1 application server, and 1 additional router for firewall and TCP adjustment. And I was thinking that in the beginning we will start with the small Minion. So small means that 1 CP plus DP will handle 220 gigabits per second. The medium size will be twice big, and the whole server Minion will process 80 gigabits per second. And to visualize this, I prepared some slides in the like phase. So here is one site architecture example. We have 3 servers. On 2 servers there are our gateways, and on 3rd servers are additional applications that we need to run along with gateways. So in this application server we have this CDR subsystem, dealers and KMS. We have some performance statistics software like Cacti or Elasticsearch, and we have GTP load balancer. because main concept of this minion architecture is that you have this GTP load balancer, and GTP load balancers actively checks if every of minion is leaving, and if not, it will not forward the traffic to it. In this phase one, we have small minions. So one minion is like one CP and two DP running. One DP is handling 10 gigabits per second. So we have 80 gigabits on one server, 80 gigabits on second server. They are connected to router on the site via 100 gigabits per second link. And the router is connected to the S1U and internet network by 200 links. In phase two, if everything is stable, we have the minions are not crashing or something like this, we can imagine that we will expand our minions. So nothing changed, aside only that the minions get bigger. So there will be 4 minions in this scenario. One is consists of 1 CP and 4 DP. And in the third phase, we can imagine that we could have 1 minion per server, and this minion can handle 80 gigabits per second. So it looks like this. So next one is campus networks. I will check if there are some questions. Okay. So the second business case that we are looking for is campus network, also called private LTE 5G network for industry. It's a full solution for the industry 4.0. We are currently running a POC for that, and we believe that our gateway from ONF can handle very well in this environment. The main assumption is that radio and core infrastructure is at customers' premises. So we put our radio resources in ODBs, and we put some of our core network elements to the customer premises, and they are tied together in order to have minimum round trip time. It's critical for these services that the round trip time is latency is very small. The other assumption for this network is that this radio is shared for private and public services. And it can be accomplished by using different PLMN. So this radio will broadcast 2 PLMNs, one PLMN for the public services like internet or MMS or IMS, and the second one is for the private industry customer services. And the scale is completely different than in FMS use case. So we have little sessions, and the throughput is less than, I could say that it is like a few hundred megabits per second. So it's completely different use case. So we need to have different scaling model for that. In this, there are several options that you can have campus network, depending how much of the packet core you want to put to your customer premises. In our current proof of concepts, we are using this option 3. So at customer premises, there is only eNodeBs and the gateway. So MME, HSS, PCRF, everything else is at our TMMPL network, and and the application servers of the user of the customer is also on this campus area. So the traffic from the eNodeBs is going locally with minimum latency in such scenario. Okay. The status of this business case is that we need new features which FMS doesn't need it. So static APN and private APN. Fortunately, we have hardware specification already, so it should be as small as possible because we have less throughput requirements and user requirements capacity. And after some final network architecture design, we are planning to deploy this in the Q2 this year. And here is some example how we are seeing this. So you have two servers on customer premises. So this box is customer premises. On the left is operator core, where the MME and HSS are. And on the right, there is a customer VPN, and it is connecting several different locations of the customer. And on this customer premises, we put our eNode B, and we put two servers. One server running NGIC with the APN, and the second server running SGX CDR subsystem and some performance statistics. Our gateway is connected to local client infrastructure via firewall and this B2B router. Okay, so that was about the business cases that we have. Now I would like to tell you about this FMS proof of concept that we have on December. Why? We want, as Michal said, we wanted to test possibility of using open source core elements. Is they mature enough and stable enough to use it, to think about it at least. Eventually, it could reduce the overall TCO cost for certain use cases. Of course, we will not get rid of the legacy vendors, commercial vendors. It's not possible, right? I think in current state, it's not possible because of the different features that were developed by years by the vendors. What we will test it? What we had? We had this NGIC running on bare metal. It was Huawei server in one silo mode. So it was one CP, one DP running together on bare metal. We connected our test lab environment to commercial network, to public MMEs and eNode Bs. And we redirected some of the FMS user to NGIC. Like Michal said, we use this charging characteristic parameter. We changed it for some users, this parameter, and using this APN redirection feature in MME, we redirected them to the NGIC in test lab. It's worth mentioning that all eNode Bs MMEs for all the country were in use. So it was countrywide, and we ran it for a month. As a result, it appeared that it is really a success. There was no complaints from those users at all. There were no software problems with NGIC, which was very strange. I didn't expect that, honestly. I thought that something will crash. I didn't expect that it will be no problems with that. During this month, our users transferred about 50 terabytes of traffic, and we selected 120 users. This is the ecosystem that was used. So in our test lab, we have 3 instances of 3 servers, Lab Minion 0, 1, 2, and 3. In front of them, there is this GTP load balancer. For POC, for simplicity, we didn't use this GTP load balancers. However, it was tested that this load balancing is working with NGIC. We used commercial MMEs and INOSBs. There was in the lab, there was this CDR subsystem connected to our FTPS client for gathering CDRs. And we used also our interconnection to internet from lab. Our router did the nothing on the side. The hardware that was used, it was Huawei servers with 2 Intel CPUs and Intel X540 series of the NICs. The timeline is like this. On the top, you have total sessions on Lab Minion 01, and on the bottom you have total traffic in bits per second. It is worth mentioning that we had 1 gigabit per second interfaces, so we couldn't do much more traffic because of that. So after a few days of the beginning, we had 100 users on NGIC, on Open Gateway, and those users were transferring about 80 megabits per second. After that, we selected 20 heavy users. It was really heavy users, and you can see that 20 heavy users raised the traffic to 300 megabits per second, like this. So it's a very good example of Pareto principle that 20% of your users are generating 80% of the traffic. After 1 week, we performed an upgrade of the NGIC because Intel found some memory leak problems in the code. We never have these problems, but nevertheless, it was advised to upgrade. We did it like we changed the redirection in the DNS. Cleared all the subscribers in the MME, and after upgrade we put them back. And after 4 weeks there was the fade out phase, and users gradually was falling down from the NGIC, were disconnecting, and that ended. Comparing this traffic to our legacy vendors and legacy gateways, I could say that it is very similar. So 100 users generated about 300 megabits per second. So it's basically the same, proving that there was no problems in the network. If there was some problems with throughput, I would expect that NGIC graph is lower than in real gateway. I did also the CDR analysis to show you some interesting things. So we have this volume limit feature, so you can configure that CDR. There are partial CDRs, so each time user download 1 gigabyte per second, the partial CDR is generated. So in total, there was 50,000 CDRs generated, and users transferred, all the users transferred 44 terabytes in downlink and 8 terabytes in uplink. I also did some analysis on heavy users. So the fastest throughput, one user transferred 1 gigabyte in 59 seconds. So the average transfer is around more than 100 megabits per second. There was some user that transferred itself nearly 6 terabytes of downlink data. I don't know what he was downloading, probably some games, but it was quite astonishing. The longest session that I found it's 14 days and 11 hours, and it is only because of the upgrade. Probably this user could its sessions could last for a month because it was never disconnected from the network. Some lessons learned from the proof of concept. The system was very stable. We had a problem with the users who slowly moves to 3G. As you know, the NGIC does not support 3G, so it is 3G. When the user goes to 3G, it is going to commercial GGSN and it stays there. It will never come back to the NGIC. It was impossible to estimate performance of the NGIC because the CPUs was running at 100%. Because of the architecture design, we are in the state that we are constantly pulling the interface, checking the interface, and the CPU is at 100%, so you don't know what is your performance, right? What is your capability? Unless you are starting to losing packets, so you will know that you hit the capacity. And we find out also this scalability models should be designed by use case. Okay, there's a question from Dominic. Is there any information on the hardware node Bs used in the campus POC? In our commercial network, we have Ericsson MME, and we have for sure Huawei eNode Bs, some Nokia, and some Ericsson eNode Bs. So, okay. So let's jump into the technical information about the new features, bugs, and the performance. This is the architecture taken from OMEC. This is general architecture. We didn't use every component for our proof of concept. NGIC, here is some basic information. You probably know all of this. There are 3 modes: SGW only, PW only on SP gateway. In our case, we always wanted SP gateway. There was no need for a serving gateway only or packet P gateway only modes. It's a CAPS architecture. Communication is not via SX like in 3GPP, but via ZMQ. It is running on the Linux and using DPDK for fast processing. That's obvious stuff. This is what was used in our case. So we had this SIA gateway split it in 2. So SIA gateway control part, CP, and SIA gateway user part, DP. And we had also this SGX billing and SGX key store components. It was also taken from OMEC. The features that was present when we started at the end of the 2018. So there was only 4G support, basic IP connectivity like static ARP or KNI, simple data forwarding S1U SGI, and multiple APN support. It was possible to configure several APNs. When we took the software, it found out quickly that we cannot do any basic test because it was never tested in telco environment. I believe it was tested in lab when you have also simulators on the other side. So we quickly find out many lacking features, many issues. Overall, this is highlighted the most important features that was developed by Intel in 2019 to make this POC happen. So first of all, this was the first test. It was lacking that the DNS were never provided by the gateway, so we needed to add it. There was only one MME supported. I don't know why. So we changed it to that every MME was supporting. UE IP allocation was not working, so it was working like you could assign IP outside of the IP pool. There was no FTAID validation. IPN was case sensitive for unknown reason. The big step was introducing the CDRs. So I think that Intel will tell about this major CPDP code rewriting, because the CDRs were generated on the DP side, not on the CP like it should be. And it was like DP lacks many information about the session, about the IMSI, about the other informations. So we added this 3GPP CDR support. It was based on the P Gateway release 11 specification, and it caused a major CP code rewriting. So it took a very long time, few months at least, to make it working. In the CDRs, there is also this volume limit and time limit functions, and also SGX secure storing and FTPS support for CD transfer. And you can also adjust the CDR file size. From other features, the delete session when the UE connects, the same UE connects twice. For example, if you have UE lost the radio signal and comes back, it could, if the previous session was not deleted, it could, deplete the NGIC session table and capacity. The timestamps were in the logs, and basic CPDP statistics was added. About the future, now in progress we have several features on the table. The most important one is lawful interception. It's not easy at all, so it's still in progress. We need 2 features for this campus network: it's private APN support and static IP allocation in APN. The next ones are from the operation point of view. So graceful CP shutdown. Imagine you want to upgrade your CP and you want to shut down, but you want users to disconnect. Zombie session support, so session timeouts, idle timeout parameters, S1U fragmentation reassembly, VLANs, stats extensions. For the future candidates, this is listed some of I was thinking of. So bitrate policing, NAT in the gateway, 5G migration to DP migration to UPF. I think that introducing SX interface, it could easily and the new interface on the 5G core, it could easily be adapted to use as a UPF. Maybe for some use case, IPv6 APN support could be added, maybe 2G, 3G, but it probably be not very likely to do that. Here is a slide from Intel, and what we are planning to do with the packet processing capabilities. I believe that on the next part of the workshop, it will be more described in details. So basically now what we have a bare metal server that is running NGIC, and we are using DPDK networking for packet processing. This year, the Linux capabilities will be introduced. So you could have on bare metal either DPDK networking or Linux networking. Of course, Linux will hit performance, of course, but hopefully not the impact. Introducing new Intel features like this ATQ and XDP, it could not impact so much. And in the next future steps, it will be adopted to run on the Kubernetes, Docker, Cloud Native, and other interesting new feature in the future deployments. Here is a list of bugs that we have detected. It is showing how much work was done. I will not tell about every one of them. Maybe this one is very interesting. DP hangs after a few hours. This was a major redesign problem. So it was about the DPDK and about the bursts and about the KNI. It was very hard to troubleshoot because it was looking like it is random. So after a few hours, sometimes after a day, the DP hangs. It was not forwarding packets. It was running, but it was not forwarding packets. And after 3 months of troubleshooting, the second major redesign was introduced in the code. There are many features added, but also there are many features missing. And here is a list of the common telco features that telco operators are used to have. And this is missing in our case because our business case doesn't needed all of them. So there are no LI support. It is work in progress, but for now there is no lawful interception. There's no bitrate limitations per user. You can work around it by using static HSS provisioning, but it's like going back 5 years ago when we didn't have PCRF. 4G only. There is no NAT, so you need to. If you need NAT, you need external router or firewall. No IP fragmentation so far, so you have adjust the TCP/M segment size on external router. No online, no PCRF, only offline CDRs for billing purposes. No redundancy. So we didn't design, it is not designed to have redundancy because of this minion principle. You have small, simple, not reliable gateway that can crash at any time, but you accept this risk. No DPI, deep packet inspection, no shallow packet inspection. Commonly it is used in telco world. And also currently we are supporting dynamic IPv4 address allocation only. So if you need IPv6 or you need static addressing, there is not here yet. And last but not least, from the operations point of view, it is not that operators are used to. So there are very basic functionalities like command line. There are no alarms, some statistics, but it's very limited. So this sure needs to be developed more for operator. If we are talking about the performance, in our POC, we use this this scenario. So one CP had 3 CPUs and one DP had 4 CPUs, and it was achieved in the test lab environments 2 megabit packet, 2 million packets per second on downlink. Depending on packet size, you can achieve from 10 gigabits to 24 gigabits. But currently in progress, we are planning to use only 2 CPUs for DP because of the asymmetry in the telco world. So downlink is always higher than uplink. So we can put some components on the uplink core and have only 2 CPUs for DP and have no dedicated CPU for the CP. So this performance will be even better. And to prove it, we also had this, we are beginning with the 5G NSA in our network. And this is an example from our commercially launched 5G Node B. And we achieved 800 megabits per second for one user in 5G. But the limitation was not NGIC. The limitation was on the radio side. So we didn't hit a limit for one user. And that's it. That's all I got. Thank you very much. I see that there are many questions. So the question is, does multi-MME support means S10L interface support? No, multi-MME means that NGIC can accept create session requests from any MME in the network. Previously, it was restricted to only one MME configured in the configuration file. Okay, are the presentation going to be available after the webinar? Yes, sure, I will provide it. The question about the deployment, is it based on the VM or containers? No, we didn't use this. We used only bare metal configuration. Okay, so that's it. I think there are no more questions. So what's next in the agenda? August, can you?
Thanks, Rafal. I think I can go next.
Okay, Samnat. So I believe we have 30 minutes today. Yes, so let's go with your presentation, Samnat.
Yep. So yeah, let me share. I'm not sure if I can cover the entire presentation in the next 30 minutes, but most likely it will overflow into Wednesday. But let's see how much we can cover today. All right. Can everyone see my screen?
We can see your screen. Thank you.
Perfect. Thank you. All right. So what I'm planning to cover today is mostly the design and architecture changes that we had to do on the code base to address all the requirements and issues that Rafal showed. He showed his requirement and design slide. However, before we go into the design architecture, I'll quickly try to cover some of the background on the stuff. Maybe it's kind of a repeat, but just for continuity, I'll just cover those quickly. So again, before we start, here are the acronyms that typically we use in all our slides for this T-Mobile project. Again, the slide and all the material, they should be available after the session. So background again, we have seen this deck, we've seen this picture maybe a couple of times already in this session. Basically what I'm trying to highlight here is the red boxes, which basically showing what was not available on the original OMEC project, and T-Mobile team specifically pointed out limitations or lack of features on these red boxes. So for example, on the S11 side, there were some features missing. S1U side, there were some issues there. CDRs, the way it was generated, for example, on the OMEC code base, the CDRs are generated from the packet gateway, but T-Mobile was very clear they wanted it from the control plane. Also, the way the CDRs were exported to the billing system, that was not following any standard. The requirement was, hey, you have to make sure it can be transferred over a standard protocol like FTP. And of course, it has to be secured. So brief background on this. So we took this code base from OMEC. I'm not sure exactly how much we rewrote. This is not the latest numbers. We should run the latest numbers and let you know. But approximately at this point, we think more than 50 or 60% of the code has been rewritten to address all the requirements and issues that we found during the T-Mobile project. Again, Rafal pointed out this very clearly that OMEC had all these VNFs and components that was open source last year. However, T-Mobile specifically, they were interested in the control plane and data plane and the billing system only. So the boxes in yellow, they're part of the OMEC, but they are not being used by the T-Mobile in the T-Mobile project. All right, so again, I'm not going into details of all these things. Rafal kind of covered it in his slide deck already. So before we go into the design and the changes that we have done, a very quick run on the issues. Again, here, if you look at the graph, there were a lot of issues we found during our development and testing. And so over the period of time, we tried to make sure we can address the issues as much as possible. Again, there was some lag between the issues getting filed and the issues getting resolved. And there's an Excel sheet attached. I'll not go through the details. When the slide is uploaded, you can always go through the Excel sheet and see in detail what those issues were and when they were filed and what was the resolution. So very critical issues. Again, Rafal did point out on one, which is the DP hanging after a few hours. But apart from that, there were other issues as well that kept us awake in the night. For example, the DP sec fault issue was a very critical one. Again, there's some issues on the KNI side where we were trying to handle the non-fast path packets through the KNI interface, and At some point of time after running like for a few hours, it used to panic out. There were some issues with the way the KNI mbuffs were handled. Again, I'll go through the design changes that we did. And of course, there were some memory leak on both CP and DP that also we had to fix. And some of these issues were observed not during our regular testing. So we have a regular quick test using a traffic generator that we have developed in-house. But when we ran the CP and DP through the Spirent conformance test, a lot of the issues emerged out. So again, there's an Excel sheet attached. You can go through those issues in detail later if you want. Okay, now let's jump into the features. Multiple MME support, SGX protected, CDRs, FTP transfer of the CDR record to the billing system over a secure interface. Per APN timer and volume-based CDRs, that was a very important feature that T-Mobile requested. As they pointed out, the APN way of handling the multiple users is something that was very critical. And it was very clear that the CDRs should be generated not only during the start or end of the session, but also based on a timer and volume. For example, every 10 seconds or every 1 hour, whatever the time interval is, the CDR should be generated, as well as volume-based, where they say for every gigabyte transferred on uplink and downlink, a CDR should be generated. So that was a very important feature. And for that, we had to do a lot of redesign in the data plane to achieve this kind of granularity on the time basis as well as the volume. Lawful intercept is a very, very critical feature, as both Michal and Rafal pointed out. In fact, the trial that was running last year at T-Mobile in the month of December, that had to be shut down because of the lack of lawful intercept interfaces on the data plane and the control plane. M-cross-N scaling of CP and DP, again, to handle varying loads, the different type of deployment and user experience. We had to also incorporate the scaling factor of CP and DP, where they can asymmetrically scale. And that is also something which is a work in progress at this point. And of course, in a commercial deployment like FMS or campus network, the gateways need to be fully Linux aware, and they should be able to be managed over Linux interfaces. All right, so that was a quick overview of what the issues were, what the features that we had to develop. Now, going into specifically the control plane and data plane design. Again, this picture that I'm showing right now is basically what the whole project was all about. So right now, in the next few slides, I'll focus on the design on the control plane and data plane side, and then I'll go into the CDR as well. All right, so talking about the design here. So the CDR flow, remember when T-Mobile came to us, right? They said the CDR flow that's happening right now, it's basically the CDRs are getting generated from the data plane, and that is not something that's as per the standard. The CDRs should come out of the control plane. And for that, we had to redesign the whole flow of data that happens inside the DP, as well as how the data for the volume and timers, they flow between the DP and the CP. And the CP is where the CDRs are actually generated for the billing system. Now, the way we did it is we looked at the data structures, we looked at the existing flow, and we had to make sure the flow can be, we tried to use the most of the existing data structures, we also had to plumb a lot of stuff inside the DP to make this happen. So now, if you look at here, right, on the top, the request where the session requests are coming, for example, the delete sessions or even the create sessions, which is shown in the middle. So the session create request, the session delete request, these are all coming from the CP to the DP. But what happens is in the session create flow, for example, the data structures are populated in the DP. And that's the data structure that's used for most of the lookups that's going to happen for the CDR generation.
Somnath, Ashok here. Maybe if, sorry to interrupt, I think as context, I'm not sure if you covered it, is the code base that we started with. So whatever is on OMEC, which we basically branched off and developed FMS for T-Mobile, the data structures in the DP are essentially the CP and DP data structures were completely disjoint. So which means that the data structures that needed to be on the CP weren't there on the CP. Essentially, the data structures on the CP had to be primarily the packet flow information and session information. So if people are familiar with the code base in OMEC today, there is a structure called session information structure. The DP has about 4 data structures. Uplink, hash table, uplink, downlink, etc. But the main point here is session information structure. That session information structure needed to be made available back to the CP. And there was no mechanism in the code base that was upstream that existed as of January 2019 that would allow that. That was the that basically caused about 60% of the code rewrite. I'll stop you, Somnath. So I think that's the context. I thought that context was important. The code rewrite that needed to happen. And what T-Mobile Poland really helped us realize was you needed a few things. One is IMSI, right off the top of my head. We have big Excels capturing requirements. Rafal, and there's another colleague of his, Darius. What they helped us realize as engineers were IMSI A, UE context is anchored to the IMSI. IMSI is what the CDRs are anchored to. However, IMSI cannot be made available in the user plane function, which is the data plane. IMSI needed to be abstracted out. So if you guys, once you take a look at the code base that will be upstreamed, there is a separation between, there is a randomization of the IMSI as available on the DP. And that randomized IMSI or the remapped IMSI comes back to the CP on which the CDRs are generated. So that roughly captures the code design that needed to happen. If you do a git diff between the code base that existed and the code base that will be upstreamed, I'm not sure you'll see much in common. Thanks so much. Sorry to interrupt you.
No, thanks. Perfect. So basically what Ashok is talking about is basically saying the kind of changes that had to be done for example, this feature was like, there was a lot of effort going behind this feature. So coming back to the details here, if you look at the slide now you see now we had to make sure that all the information that's required for the CDR flow is available between all the synchronous requests that's coming from the CP as well as the asynchronous updates that's going back into the CP. So for example, on the extreme right side, if you see, there are 2 different aspects of the CDR generated from the DP, apart from the synchronous session deletes and session creates. And those are the CDR updates due to the volume threshold and CDR updates due to the time threshold. So those independent modules is to now they pump the, based on whichever threshold has been reached, they pump the session ID through a ring that's consumed by a process engine, consuming the session ID from the ring, then again going into looking into the data structures, finding out the relevant information, and sending the synchronous updates back into the CP. So, so these are the changes that had to be done. Again, as Ashok mentioned, he rightly mentioned, when you do a diff between the original OMEC DP versus the new DP for T-Mobile Poland, there'll be like a lot of changes you'll see that had to be done to achieve this feature. All right, so with that, let me quickly see if there are any questions. Okay, mostly answered. All right, so going to the next slide. So next slide talks about the cores being used at the DP, the way it was originally used in the OMEC code base, right? So in the original OMEC code base, you see there was one core handling the uplink traffic. So the core consumes packets from the S1U interface, does the processing, sends it out on the SGI. Again, but the same core also does the K9 handling. And on the SGI side, I mean the downlink side, another core doing the same stuff, consuming from the SGI, doing the GTP processing and K9 and sending out.
Sorry, Somnath. I think you want to say the issue that we faced here. This was the biggest issue that we faced.
Right. I'm coming to that.
Okay, fine. Sorry.
So this is the original design, and there is to be a third management core that is to handle the management packet handling, the ARC packet handling, and other stuff. Now the issue here is, if you take a closer look at the slide, right? Recall that the issue that Rafal mentioned, the DP hanging after a few hours, and that was an issue that we actually spent a lot of time to resolve. And eventually what we found out with this current design is, at some point, if you look at the flow, two cores are trying to access the same SGI or S1U ports for sending out packets. And it works for some time, but it may eventually fail, or it may cause some kind of deadlock if you are not implementing software locks in your code. So now if you look at this slide again, you can see the uplink core as well as the management core, both are trying to access the SGI side, transmit side port to send packets out. That's on the SGI side. Similarly, on the S1U side, you can see the downlink core as well as the same management core trying to send out packets on the S1U side. And DPDK clearly says in its developer docs that ideally the software should implement a lock if they are trying to use the same queue to transmit out. One solution could be saying, hey, why don't we use multiple queues on the NIC to transmit those packets, right? That works, but the problem is when you want to run these instances in a VM, we had a lot of issues exposing all the queues through the NIC. And we basically said, hey, this could run, we could somehow put some workarounds and make it run inside a VM, but we want to make the solution generic enough so that it can be run in any kind of environment. So based on that issue and our observation on the old code base, we had to redesign the whole flow to make sure there are no conflicts, at least from the DPDK side. And all the cores responsible for their processing, they do not conflict with each other. So now let's look at the new flow, which is in the T-Mobile code base. Again, when you get the code base, when it's available on GitHub, you should be able to see these changes very clearly. Now we have a dedicated uplink core and a dedicated downlink core. Now you can see there is no conflicts between the uplink core and downlink core. The same uplink core, which was also receiving packets in the earlier design, but in this new design, the uplink core is also responsible for doing the GTP echo, the KNI push, as well as handling the KNI receive at the SGI side. And this core is doing all the job all by itself. And for flows that it needs the response to go back on the same interface. For example, it receives a GTP echo request from the S1U, but the GTP echo response needs to go back on the S1U TX, which is being handled by the downlink core. So in that case, what it's doing is basically we are using the Linux memory manager for making sure that accesses between the cores are synchronized enough. So we are using the heap through which it can be transferred. The GTP echo request would be transferred. Just the information is transferred there. The mbuf is freed up. So there's no mbuf conflicts there. And the SGI or the downlink core, it manages, handles the GTP echo response, creates a GTP echo response packet and sends it out on the S1U. This is without the ARP flow. That means if you have static ARP configured on the system, if you want dynamic ARP, that's also very simple. You can see the delta. The same flow, but in this case, the downlink traffic, for example, it receives S1, it receives the ARP request. Again, it gets the request, extracts the request information, frees up the mbuf, sends the information into the heap memory, and the downlink core gets the response from the heap memory, forms the ARP response, and sends it out on the S1U interface. And that's exactly symmetrical operations happen on the SGI side. So this design, basically what you're seeing here is instead of using software locks in our own code or getting into any kind of conflicts for the DPDK, RX or TX, we are using the Linux memory managers, the heap manage. Basically, we're using the Linux heap for making sure that we are able to transfer or exchange information between the downlink and the uplink core without any locks. All right, so let me see if there are any questions before we jump into the CDR design. Okay. So the first question, okay, how many interfaces are supported on S1U SGI? Yes, this design that we are looking at, we are supporting one S1U interface and one SGI interface. I mean, is it like single physical interface maps to S1U SGI? Can we group multiple physical logical groups in interface in a group and treat them as a S1U SGI? Okay, for here, we are using DPDK. So we depend on DPDK's binding. So in this particular code base that will be released, you will see we only support one S1U and one SGI interface based on the way the DPDK binds the interfaces. As Rafal pointed out, we are also working on other developments and advanced features where we can combine multiple physical interfaces on the S1U as well as SGI side that could be logically grouped as a single interface. Another question, should the blue color show S1U RX?
Yes, there is a typo on the left, on the upper left. S1U RX.
Oh, okay, yeah, that's right. Okay, thanks for pointing that out. Yes, that should be, yes. Perfect, thank you so much. All right. So with that, ideally what I want to do is I want to cover the CDRs, the design and the changes, but I think we are almost at the top of the hour. I want to basically take a logical break here. The Wednesday session, I think we should continue with this, and we can continue with the design of the CDRs. It also involves a little bit background on SGX, why SGX and how SGX, Intel SGX technology helps secure the CDRs, as well as we'll go into the detailed design of the whole security aspect of the CDRs. All right, so with that, I think any questions? I don't see any more questions on the question list. I can hand over to Dennis or Aus. You want to close this today's session?
Thank you very much for joining us today, and thank you to our speakers. We appreciate your joining us and invite you to the second half of this workshop, which will take place at this Wednesday at 7 a.m. Pacific time. We hope you'll join. You do need to register separately, so please do so. We will be making this recording available to everyone that registered, as well as we will gather the slides and share those with you as well. We look forward to seeing you in a couple days. Thank you.